In Houston, Texas. Welcome everybody to another program of the Mini Geology radio show where we put in touch our beloved discipline of geology with society at large. And today I'd like to bring you a great explorer to talk about the unconventionals. You know, we had an unconventional revolution related to the energy, specifically about the petroleum systems. So, the unconventional revolution, what is it about? We are going to catch up with that. We are going to see in specific the geology of the unconventionals. There's many other things related to unconventionals, including the economy and geopolitics, but we're going to touch mainly on geology. So welcome everybody to my dear guest, Fernando Sanchez.
Hi there.
Hi Fernando. Here we are in the studios of KPFT with Mini Geology HD2 channel. And today we're going to talk about the unconventionals, the production of hydrocarbons from mudstones, but also tight sandstones, has improved the economy in the United States and Canada, has decreased the greenhouse gas emissions, and has created also geopolitical implications. Just remember the reduced addiction from the Middle East oil. So what has happened around 2008, 2010, 2012 is known as the Unconventional Revolution. And the Unconventional Revolution has modified also the studies of geology, the job market related with people that they are professional geologists. So today we'll talk about the importance of the geology in the unconventionals. Fernando Sanchez here with me is a great friend, but he's above all a great explorer, and he's practical, he's pragmatic, and he transitioned from the conventional to the unconventional. So, Fernando, how were you caught in this unconventional revolution?
Well, I guess I've been doing conventionals most of my career, which is very long. It spans nearly 30 years now. And I believe it was in around 2010 when we realized it was becoming obvious the unconventional revolution, as you mentioned. You know, operators suddenly activating provinces in the U.S. that were not that great producers, and suddenly they were producing a lot of gas and oil. So we were kind of caught into that and started developing our expertise. And that happens within the span of 4 or 5 years that we kind of understood what unconventionals were about and what mattered, you know, what made them tick.
Was it very difficult, the transition for you from being an explorer in the conventional to being an explorer of the unconventionals?
It was a little confusing in the beginning, yes, because as a conventional explorer, you think of 3 or 4 elements which are mostly geological related. You know, you think about trap or structure, what traps the oil. You think about reservoir, where the oil is contained. You think about seals that kind of block the migration of the oil further upwards. But the unconventionals are self-contained often, sometimes are not. But one of the kinds, the shale ones, are self-contained, so you cannot reason in the same terms anymore. The oil or the gas are just there, and you just need to extract it. Now, that the unconventional revolution kind of was made possible through some kind of technological breakthroughs that took years to discover and implement efficiently. And those are the famous fracking process. Fracturing a rock has existed in the conventional world for a long time. It's on routinely in conventionals. But we were talking about a much larger scale fracking, such that you could create your permeable system within the rock. And that took a while, you know, for people to investigate, many trials and errors in the U.S., about what fluids to use, what amount of sand to use. The sand is what goes in with the fluid and kind of blocks the created fractures so they don't close down. And so that took a little while, and in fact, it was the combination of fracking and horizontal wells that kind of made the whole thing possible economically. That's when unconventionals took off.
Horizontal wells also was another technique that was used in the previous year. So it was the overlapping of these two, let's say, relatively old technologies.
Exactly. Yes. Yeah. The optimization, the study of those techniques, how to blend them, that made possible around 2010 to have some economical wells. Before the process existed, but it was uneconomical. So companies didn't tackle it.
So if we want to define the unconventionals for the listeners that they have heard about unconventionals, but they don't really know what exactly is. Unconventionals, at the beginning, is just an adjective that engineers, they maybe use in order to define how to produce, and they produce in an unconventional way. So am I correct if I define the unconventionals as oil and gas bearing formations with permeabilities that are so low that economically meaningful production needs to be realized through the horizontal drilling and the hydraulic fracturing that you were talking about?
Yes, that's correct. The term unconventional is it describes this type of reservoirs but also this type of procedures, to exploit them. The reservoir part you touched upon is very important. Those are reservoirs that are not new reservoirs or anything of the sort. They existed through conventional exploration. You sometimes went through formations, drilled through formations that gave you shows, suddenly a kick of oil, or a little bit of gas. But people did not stop by them, did not produce them because they were tight. So they didn't have characteristics such that favor production. They were very tight, very impermeable, and it's only through the stimulation that those kind of become important producers. So the term unconventional refers exactly to those reservoirs. There are two main kinds: shales, and shales are essentially they're skeletons from animals that live plankton. And other macroscopic animals that live in the sea, actually, within the photic zone, within the first, dozens of meters. And when they die, they kind of drop to the bottom. In normal conditions, they are either consumed by others or they corrupt, decompose on the bottom. But there are certain conditions in geological history that lead to stratification of the water, as such that there is very little vertical circulation. So that creates a column of water at the bottom which is stagnant. It doesn't move. And those conditions have very little oxygen. They are called anoxic. So under those conditions that happen in the Earth for various reasons, global reasons, throughout the Earth mostly, you have these source rocks, these shales that fell into the bottom, did not decompose. They preserve all their organic matter, and that's what gives rise to the hydrocarbons.
Before moving into the details of the unconventional and the geology of the unconventionals, I would like to touch on you being an explorer. Mm-hmm. So I would like to know, what does it mean for you to be a professional explorer? You've been dedicated, your entire life has been dedicated to this activity. Being an explorer, what does it mean for you?
Well, it's something you discover as you go along, and certainly it becomes very clear what it is once you drill a few wells. Before that is maybe a little theoretical, but it started as many things. I got a job. They kind of threw upon me a few programs that I needed to do as I was a trainee. I was mainly calculator things. At some point, somebody said, we need help with this interpretation. And I said, what's that? And they showed me the seismic lines. Seismic lines are cross-sections of the Earth done through seismic methods, like similar to sonar or radar. So I was amazed. I was told, you have to try to interpret this, try to make sense of these, see whether there are traps in here. And that's the way I started. And as you get more experience, then you understand the geology of a certain area, then you can correlate things that you see on those seismic lines with things that you see currently, such you can suddenly detect reefal features, like the reefs we see in the Pacific, the coral reefs. You can detect aeolian dunes. You can see so many things. So in some ways, interpreting or exploring is a very intimate process of you and the data. The data talks to you, and you kind of stop and think a lot. And ultimately, you develop a concept, which is usually an idea you have, an idea that involves a combination of reservoir, of trap, and you develop the idea, you convince yourself that it's possible, you assess its risks, because not all ideas are possible, and then you present it to management, and management, if they like the idea, they would say, well, we're going to drill it, we're going to invest some money drilling this well. When you drill the well, then is when the nature talks back to you, if you're lucky, which doesn't happen all that often, maybe 30-40% of the time, or maybe less than 30, then you discover what you prognosed, or some variant of it. You discover hydrocarbons, maybe not exactly as you expected them, but then you have all this information that the Earth is telling you. The things that you thought that were misguided, other new things. That's the most interesting part, when you discover new things through the drilling bit. Yeah. And oftentimes you just don't have any success. So maybe you discovered what you prognosed, but they were not hydrocarbons. Or maybe you have a completely different surprise. Things are very much deeper than you thought. They are not at all what you expected. And those lessons are very important for an explorer. It's as important as having success. Learning from those failures and listening to the voice of nature that tells you, in some ways, it calibrates you for a further in your career, to become more realistic about things, to develop intuition about things.
So, and the epiphany to discover that you are an explorer, it occurs when you drill. That's one of the most important activities of an explorer.
It's the ultimate one, yeah. I mean, you can come up with we do studies, we can come up with and scheme a story of the evolution of a certain piece of the Earth in a certain time, in geological time. So we can develop a report and maybe speculate that, sometime 150 million years ago, this was a sea, because we do see expression of those seas, ancient seas. And then it became a desert, and then it was folded up and it became a mountain. You can of course develop those hypotheses, those theories, and that's done routinely. And that's kind of more the academic sort of geology, or the understanding of the geology. That's very important, the understanding of the geology. And out of that comes the exploration opportunities. But I believe explorers only made once they've been exposed to the calibration with nature. Once you have seen your theories either proven or disproven by the drill beat, is what makes you mature and what makes you an explorer.
Well, is it the same for an unconventional explorer?
It's a little different, because unconventionals they don't have the geological risk that conventionals have. Conventionals have several, 3 or 4 risk elements that I mentioned before. The presence of a trap, the presence of a reservoir to hold the hydrocarbons, the seal to block their escape, and other things. And unconventionals, they have less geological risk. Once you know by perhaps outcrop geology or a few older wells that there is a nice shale down there, you do your analysis and you realize it's a shale with high organic content and therefore likely to produce hydrocarbons, is mature enough to produce hydrocarbons. They're just trapped there. So once you establish all that, then you can more or less be confident that through a certain extent, aerial extent, which can be, I don't know, hundreds of square kilometers, the resource is going to be down there. So shales do change regionally, but slowly. Conventionals change rapidly. Once you are away from a structure, it's all water. You are within a structure, you find the hydrocarbons, oil or gas. So unconventionals have lesser geological risks to consider. There are a few, and you should address them before proposing any unconventional venture, of course. The unconventionals, the risks are oftentimes commercial, because that's one thing that very unique to unconventionals is a very integrated business. For unconventionals, well costs matter. The presence of infrastructure, pipelines, and facilities in a basin, so you don't have to invest in them anew, matters. Fiscal terms matter. Unconventionals require sometimes dedicated fiscals that kind of made it easy to invest in those risky investments. And other things, prices, etc. So there are many things that unconventionals is often described as a business of margins. The little margins matter. A little cheaper well, a better term, one less % royalty, $1 more in the price, it starts mattering. So that's the commercial risk of unconventionals. In fact, it's been tried in several places, many different places in the world, and it's only worked in a few that have a very sort of unique combination of characteristics, which are often surface related and economy related, that made them succeed.
In conventionals, it's easy to understand when you fail. You have a dry hole.
Yes.
When do you fail in the unconventionals?
That's a very good question. It'll take more time to understand, because we normally consider like 3 phases for unconventionals. One is the exploration or the play validation. A play is a concept. The Vaca Muerta play in Argentina, for instance, there is a formation called Vaca Muerta, which is a very thick and organic rich shale. It's very black. When you hammer it, it smells like sulfur. It really has generated a lot of hydrocarbons, so you know it's there. But it's better in some places than in others. And so you have to kind of assess all that. That's the play validation part. You validate the play of the Vaca Muerta, drill a few wells, and determine that the Vaca Muerta, the source rock, is kind of certain quality, which is appropriate. It's got a certain porosity, a certain hydrocarbon content, and so that's the initial part. So far, you don't know anything, only that the resource is there. Then there comes the second part, which is called oftentimes piloting or appraisal, in which you focus on the best parts that you have through your exploration outlined, and then you drill more wells which are close to each other. They are called pilots. They are usually horizontal wells, separated by just a few hundred meters. You typically drill 2 or 3 of them, and you produce them. Through this piloting phase, you then establish whether those wells are productive. So you establish productivity and commerciality. I guess it's only at the end of the pilot phase, which might take from 5 to 8 years. And after a significant amount of production, maybe 2 years producing those wells to see whether they suddenly lose strength in production or something strange happens to them. So it's only after these 8 years that you know whether you have failed or not, commercially failed. Whether it's worthwhile to engage into a massive investment to develop the resource, or you should just quit.
For the sake of curiosity, what are the other 2 phases that you were describing after the exploration phase and the piloting phase?
There is only one phase, really. It's called the development. And during the development, you drill many wells. You drill maybe every square mile. We call them, the wells are drilled from pads, what we call pads. A pad is really a piece of an area, usually maybe a kilometer square or so, or less, that you flattened, and from there you drill a number of wells, maybe eight horizontal wells. And so each of these pads have your 8 horizontal wells. They probably have space for facilities to separate the water that you produce or the condensates from the gas and other things. You need to have a space for all the trucks that are coming back and forth quite often in unconventionals. And these pads are drilled, I don't know, maybe one every mile or one every 1.5 miles. So you have to drill a lot in general, and that's called the development phase. Yeah.
Where is the importance of geology in these 3-4 phases that you have been explaining? Actually 3, the exploration phase, the piloting or appraisal, and the development. Where is important geology? Or where is more important?
Yeah. Well, geology is important in all the 3 phases, of course. In the case of unconventional, geologists and engineers work very closely. For instance, these horizontal wells we call navigation. They have to navigate through a space of a length from 1 kilometer to even 3 kilometers. Horizontally, yeah. And they have to follow a certain formation, which may be, I don't know, 150 feet thick, 50 meters. So they have to be really precise navigating that formation, staying within it. The moment they go out of the formation, they go into formations which are not hydrocarbon bearing or interesting or of worse quality. So, and that usually leads to failure of the well. So that's where the geologist and the engineer need to work together. The geologist need to tell the engineer where is it navigating. The geologist needs to ascertain before whether that formation is broken up by faults, what we call faults, which are breaks in the subsurface that displace the formation maybe a few meters. The geologists, of course, need beforehand kind of to outline within that source rock what's the sweetest part, the part that is more porous, the part that's got the better hydrocarbons. So geology is very, very important, but in combination with other disciplines as well.
So geologists that they are studying and working in the unconventionals, they need to approach the engineers more than the geologists that they work in the conventional petroleum systems.
They usually work a lot more close together, yes.
What should we know, we geologists, what we should know more than our colleagues in the conventional world in order to talk with the engineers?
Yes. Well, we have to know a little more of their language, of their needs. You know, the engineers speak a certain language, depending what kind they are. They could be reservoir engineers, engineers that deal with production of wells. They could be development planners, which deal with where to put the facilities, the different paths, etc., etc. They can be drillers, the people who drill the well or complete the well. Completing the well is making it ready to produce, including the famous fracking process. So the geologists need to work together with all this closely, with all these people. They need to learn the language, need to know what they need to know. So the information can be provided in a certain pragmatic way to them, not in an academic fashion. Engineers don't really care about big stories about geology.
What do they care about?
Well, usually about details. They want to know at what depth you're going to find something. That also happens in the conventional world, of course. In the conventional wells I drilled, you had a drilling engineer that will ask you for a prognosis. You have to tell him or her at what depth you're going to find what. It's going to be a limestone at 2,000 meters, and then a salt, etc., etc. They want the details, and they kind of held you accountable for it. So if you didn't find what you prognosed at that depth, well, they were kind of concerns. And so, but in conventionals is even more. You have to work more closely with all these people. I think the new geologists of the unconventional world need to be pretty well rounded, not being able not only to talk about geology, but also to know a little bit about reservoir engineering, to be a bit quantitative as well, to be able to do some maths.
Is more the geologists that they approach the engineers, or vice versa?
No, that's all. The geologist usually generates the opportunity. Is the first one. The geologist comes up one morning to his boss and said, listen, I and the team have been looking at this. This looks good. We would like to propose a venture here. And then, if management agrees, then that's when engineers come in, and they will look into that in terms of more leading towards the possible economics of the area. So the reservoir engineer will ask you certain questions, how porous this is, how permeable. Permeability matters a lot. He will come up with an estimate of production profiles, how much will a well produced. The development planner will then ask about, the surface characteristics. Are there rivers here? Are they mountains? Is it very inhabited or not? Is there water? Is there not? Are there communities that could be affected? And then the development planner does his job as well. Eventually, the economist takes hold of the whole thing and estimates how lucrative, how prolific, how economical the play would be. And then you go ahead and do it.
What is the hardest things in the work that you do as an explorer in the unconventionals, in this description of the several phases and in your daily job?
I think it's usually the integration part. You need to work, as I said, closely with people which have other disciplines.
Like which disciplines?
The reservoir engineers, the development planners, the petrophysicists, geochemistry. Maybe in that respect, it's important to highlight. You ask about geology of the unconventional geologists. There are some disciplines that were considered kind of core or very specialized for the previously, years ago. For instance, geochemistry was one of them. A geochemist was somebody very specialized that kind of understood the type of kerogen on the rocks, what they would generate, etc., etc. Now they are extremely important. To understand the shales on a geochemical perspective, their hydrocarbon potential is extremely important. So the new unconventional geologists need to know more about, for instance, geochemistry, need to know more about petrophysics, which is the assessment of reservoir quality through logs, through curves, and need to know more about reservoir engineering, how these rocks are going to produce, need to be aware of surface characteristics, where can you put your well paths, where can you advise the development planner to put them. So that's maybe the more challenging part of the unconventional world, is the fact that you work usually under some pressure to interact with others. Usually the fast is also more than conventionals. A conventional well, you can take maybe years to prepare. You drill it, and if you have a success, it might take maybe 5, 7, 10 years until you put the facility there in the water, floating production unit, for instance. The unconventional world is faster. You need to go and make deals before the price of land rises. That was observed in the beginning of the unconventional world, back in 2010 or so. The price of land in the U.S. was relatively economical. As soon as there is a resource there to be exploited, the companies rush into it, and which raises the price of the land quite significantly. So the unconventional world it's faster in general. You have to try to be first to places or second. Yeah.
So in this hard activity of trying to be rounded, which means understanding other disciplines, including geochemistry, petrophysics, reservoir engineer, and understanding about the surface, the geomorphology of land. How did you learn? How did you, when you moved from conventionals to this new world of unconventionals, and you had to learn these disciplines, and you had to interact more with these other professional figures, how did you learn?
Mm-hmm. Well, usually because we worked very close to each other, so it was through talking to them. Once every often I did some reading, etc. Refresh my knowledge or learn something new. But it was oftentimes just through work, discussing in what aspect they were contributing, the things that mattered for them, the things that they look for, learning the language. In some cases, being very close to people who were developing methods. Reservoir engineering is one discipline that is evolved fast, to understand unconventional production, how the reservoirs behave. So I've kind of witnessed some of that evolution through with engineers. The way they were thinking, the way they were modeling stuff, how would they change their approaches, depending on some well results. And it was a matter of kind of keep track with it, follow all that, and understand very well what they were trying to do. So that's the way I learned. It's through interaction with others.
Do you think that the others that you just mentioned have been mastering other disciplines, do they understand you as a geologist as well as you understand them?
Well, because that's difficult to say, really. I think it depends on the individual a lot.
Okay.
So some individuals are very specialized, and they like what they do, but they only do one thing. There's still some people like that in the industry. In general, the people tend to be a lot more open towards others and curious about other people's specialty. You oftentimes see reservoir engineers trying to talk about geology, and sometimes you have to correct them because they might say things which are simply a little naive. But at least the curiosity, the intention is there of talking the same language and all that. Yeah. All this is true in the conventional world. It's not a unique unconventional feature, but it's more accentuated within unconventionals.
And in the unconventionals, to be an explorer as you are, which kind of geologist you have to be? So you have to be a geologist, first of all. Among all these different professional figures, you have to be a geologist in order to lead the exploration. Is that right?
Yes, that's correct. Yeah.
Which kind of geologist? Could you be a sedimentologist? Could you be a structural geologist? What is preferable?
Oh, I understand, yeah. It's kind of difficult to say because it's the same thing. A good unconventional geologist is somebody who is maybe foremost a reservoir person, a sedimentologist, somebody who understands how the rocks were deposited. That may be the most important part. What led to a source rock, what conditions led to or to a tight sandstone. Second to that is what we call the genesis, the cements. Somebody who understands how cements are deposited in the rocks. Those cements sometimes occlude rocks. They kill the porosity, they kill the permeability, and they create by not killing it completely, but only partially, they create a resource which is called unconventional resource. The oil and gas are there, and they don't follow normal rules. They can be in strange places, but that's what makes the resources attractive. So sedimentology, the understanding of cements, I think next in line would be structural geology. Structural geology matters for unconventionals. You kind of like places that are not very structured, as opposed to conventionals, where you often look for a structure, or nearly always, and you don't care if it's very structured. Maybe it's even better. Good news if it's very structured. It's very deformed. In unconventionals, we generally try to avoid these complications, and so being a good structural geologist matters too. Also, because an important part of unconventionals is the fracturing of the rock. And the way a rock fractures has got to do with the stress field that the Earth has. The Earth is compressed in a certain direction, depending on the place, or is extended in a certain direction. For instance, in the Gulf of Mexico, there is extension. The Gulf of Mexico is expanding, so there is an extension there. In other places, Western U.S. or close to the Andes, it's compression because of the Andes. So, and it's got a certain direction, east-west. So, understanding the stress field is important to develop an idea of how the fractures are going to grow, how the new fractures you will make are going to develop. Are they going to be north-south, or east-west, or how? So that's kind of a part of the structural geologist too, or what we call sometimes geomechanicist. Is somebody who combines structural geology with understanding of rock physics. How competent rocks are, how well can they fracture. Some rocks are very, very tight, they fracture badly, or some rocks are so soft, so ductile, you cannot fracture them because the fractures close. So a geomechanicist understands all that, the nature of the rock, the stress field, etc.
Fernando, what is fun about your job? What is the funniest part? What do you enjoy in your daily job?
Well, I think certainly the interaction with people is very important. Being in touch with other team members, with other specialties, learning from them. Making trips together to places, to see a new resource or a new company. That's a lot of fun, the things we create together. I think in a more personal perspective is and that's also true of the conventional world. What I always liked, what always kind of motivated me to go to work is to have ideas there, you look forward to go to work because you will look at rocks, you will look at seismic, you will read something maybe, something that somebody has written about a certain area, and you will make connections, you will develop ideas, and out of those a concept will arrive, a proposal, a hypothesis, and eventually, ideally, a well or a venture.
So is it true that in the offices you still do that job? It's not just about meetings and emails and politics.
Well,
how much time do you have to do that?
There is a lot of that. A lot more than 10 years ago, I would say. I don't know why, but meetings are kind of very, very abundant these days. It's like people need to meet to decide certain things that you could decide on your own, perhaps, but they still want to meet. Some are useful and some are just redundant. But in spite of all these meetings, we do still have time to, ideally, have time to work and think. I mean, otherwise, a geologist's work doesn't really make any sense. A geologist doesn't discover hydrocarbons by sitting in meetings, It discovers hydrocarbons by reading, by talking to others, by visiting places.
Squeezing the data.
And by squeezing the data. That's right, yeah. So without this creative process, without the time to think, which I think we had more in the past than now, another thing that happens now is also the presence of very efficient programs that do your work. What in the past will cost you maybe some time because you have to go line by line, doing it, interpreting the lines, seeing what you...
You're talking about a 3D seismic volume.
Yes, and nowadays, oftentimes you have volumes that can be interpreted automatically by the system, by the machine. That leads to a certain attitude of, which is difficult to describe, is a little less creative. Is more efficient. It emphasizes producing maps very fast, the quick turnaround of things. And maps are great, but also being able to look vertically, to think in terms of sections, what happened in the Earth through time. That's something you don't develop by pressing buttons. You have to look at the section and half dream about what you think you can see. You need to scratch your head a little bit. Shall I follow this marker, this horizon, up or down?
You should own the data that you have.
Yes.
You have to know every single bit of it.
It's desirable. Yeah. Oftentimes the people that work in maps is interesting because they can produce a map very quickly. But you ask them, okay, that's great, but how did the Earth look like on this part of the map? And sometimes they don't know that because they think in maps. They don't think vertically. They haven't taken the time to go through the different lines and struggle a little bit. So I don't know. This process shouldn't be lost. The creativity process, all that,
Fernando, I'm gonna throw you there disciplines of geology. I would like you to comment on them about their importance and the meaning, why they are useful as in the unconventional world. You have already done it for some of them, but I would like to repeat them, just a couple of sentences, so that the listeners, they can understand if they are studying a specific discipline, what they could do for this unconventional, if they will. For instance, sedimentology.
Well, sedimentology is important because rocks are variable and rocks depend the way they sedimented. It leads to variations in rock, and there are sometimes what we call phases variations, which is an entirely different type of environment. So sedimentology, or the understanding of the internal kind of fabric of the rock, it's very important.
Why?
Because it determines it allows you to assess the porosity. It allows you to predict where the best porosities might be. If you are dealing with a fluviatile system, for instance, you might want to go to point bars or perhaps to mouth bars, on a delta, and you should avoid the bays and all that. So having the sedimentology view in mind is very important,
What about stratigraphy?
Stratigraphy as well. I mean, I would say this similar considerations to sedimentology would apply. Perhaps stratigraphy is more could be more or less quantitative than sedimentology, but I think they both matter equally. Yeah.
Correlations, maybe wise. Correlation-wise.
Correlating wells, etc., yes.
Petrography.
Petrography, it's important too, because through petrography we see the cements that exist in a rock. We see the mineralogy of the rock. If the mineralogy can or cannot help with unconventionals in particular. Some as I said before, some rocks are too ductile, too soft to be able to be fracked properly. So, and that also through mineralogy, whether you have quartz or you have calcite, or so very important, and the patterns as well. Yeah.
Petrophysics.
Petrophysics is essential because through petrophysics you take a well and through curves you measure the porosity, you measure the permeability through core analysis. So you take a core, you measure certain things through sometimes very long experiments that will tell you the permeability of a rock. It will tell you the saturation of the rock. And you will also will highlight, as an important part of a petrophysicist, within a certain formation, what are the best parts for you to drill your horizontal well. That's called a landing zone. So the petrophysicist, in conjunction with others, also determines that.
Geomechanics.
Geomechanics is very important because for unconventionals you need to frack and frack properly. Those fractures are sometimes poorly understood, the way they developed. They depending on the stress field and depending on the alternations of different layers in the earth. For instance, alternations of very soft and very hard layers, quick alternations, and that's done sometimes through geological history, will lead to a certain special development of fractures. You know, when you create a fracture system, those fractures want to grow in a certain direction, but if they find an obstacle, they will deviate. So, for instance, if they grow vertically and they find a competent layer, very competent layer, will then try to maybe not to frack through the competent layer, but to deviate and become horizontal, which is not as good for production. So geomechanics are important to understand, you know, how a rock will fracture and how much of a rock you think you can fracture.
Structural geology.
Important also for unconventionals for the navigation. You know, if you run through faults that can offset a reservoir, then your horizontal well will kind of go out of formation. It'll drill another formation. So a structural geologist can actually tell you beforehand whether you are going to find many of those fractures there, faults, or little, and help the navigation. Another thing that they do is to through structural geology is assessing the natural fracture systems. And you know, there are natural fractures in places which are deformed, are very important natural fracture systems. Those can contribute to the production of hydrocarbons from tight rocks, or can actually hamper it, make it more difficult, by bringing perhaps water from deeper down and flooding reservoirs with water. So that part, whether things are going to be fractured, naturally fractured or not, a structural geologist can do.
Geochemistry.
Geochemistry, as I said, used to be a very specialized kind of discipline. It's very important now. They assess the hydrocarbon generating potential of a rock. So how much organic matter did it originally have? How much of that kerogen has been transformed into hydrocarbons? The phases that a source rock might be generating, because they can generate oil, or if they get a little hotter through time, they can generate then gas and condensate, and if they get very, very hot through time, they can only generate dry gas, methane. So a geochemist will tell you all that. They will tell you about the potential of the rock to generate, what type of rock it is. Is it a marine source rock, you know, like the ones I described, skeletal rain within a sea? But there are other types, you know, of source rocks. Coals can be a source rock. Vegetable material can be a source rock as well in a delta, which generates a different type of hydrocarbon, more gassy. The carbonaceous material, the vegetable material, generates more gas. So a geochemist can tell you all that.
Basin modeling.
The basin modelers are important, and at some point I think they were, especially for conventional world, they used to be very, very powerful people, very important. They would create or destroy hydrocarbons by the touch of a button. Essentially what they do is to model the Earth through time. So they take a source rock and they bury it, you know, at a certain speed. They put certain layers on top of it, which are more or less conductive of heat. As the rock is buried, it gets hotter. And then as it gets hotter, it transforms. And the kerogen transform into hydrocarbons. A basin modeler can can tell you, how certain parts of the basins might be generating oil or gas or nothing at all.
And what do we need to know better in the unconventional exploration? We mentioned now a dozen of these disciplines. What is, according to you and your experience, something that our listeners should investigate in? What the researchers, the profession, they should understand better in order to have a better unconventional play or find a better unconventional play?
Well, sedimentology, we mentioned before, is very important, because what we found is that the source rocks, which are really deposited in the bottom of a very calm sea, so there is no waves in there, there is hardly animals, is flat, and is calm and silent and cold, and so one would think, well, nothing might be happening now here. It's all pretty. It's going to be pretty uniform for hundreds of kilometers. But what we have seen is that oftentimes these bottoms of the seas had like little highs, maybe because there was a reef there, an older reef, or a batholite, which is a volcanic thing deeper down. So they were not flat for starters. They had reliefs. We have also seen that oftentimes storms kind of are felt, very strong, storms, tsunami type, are felt at these depths as well, which are usually 100 meters or 200. We are not talking kilometers. And so they are actually quite variable, these source rocks. If you look at them in detail, they are far from uniform. They have all sorts of interesting things. Sometimes some members are even absent because of these paleoreliefs I was telling you about. So certainly a better understanding of sedimentology of the rocks will be very important, yeah.
And now we have talked about all of these disciplines, thinking that we have a play and we want to understand the play. But if we step back, somebody that has nothing to do with exploration may ask, well, how do you decide where to explore? So let's say you're an explorer. You have the entire globe you can explore. Where do you start from? Who is telling you where to go? North, East, Africa, Asia, America. How do you decide that? And then once you decide, then you decide it is this country, it is this region. I'm going to try in here. How does it happen, all of that?
You mean unconventionally or
yes,
or conventionally?
Unconventional.
Unconventionally. Okay. Well, I think first of all you probably need to understand the fiscal terms of different countries.
What is a fiscal term?
Fiscal terms are royalties. So royalty is something you pay to a government in exchange for selling hydrocarbons in that particular place, all the countries.
So first you have to find a place that is cheap. That's what you mean.
You have to. Unconventionals require certain conditions because they are very investment heavy. So certainly you shouldn't go to a place that in which most of the value is taken at the wellhead by a high royalty. These high royalties happen. I mean, sometimes they are determined by the political system. And with high royalties, only very productive wells work. Wells that produce 25,000 barrels per day, something like that. Those are conventional wells. Unconventional wells are not that productive. So you have to look for a place where the terms are favorable. Otherwise, you just don't have a business. And so I will start kind of scanning the different countries, etc. Which countries offer the more favorable terms? Then surface considerations are important. You of course want to avoid jungles and environmentally sensitive places. It just doesn't work. An unconventional development in a jungle, for instance, is unthinkable. You need other type of surface. Low population density,
flat,
plenty of water, flat, etc. So you kind of scan through all that again, and once you have determined the places, then of course you look for the resource. So you look for the presence of good source rocks.
How do you look for a source rock? You're right there. Where do you look at the very beginning? Like legacy data, literature, or you go to the outcrops?
Well, if you know nothing about an area, there's always articles about all countries. Geologists have been everywhere, and they've written things about. So you read all that, and then you probably should get in touch with universities in the place, because those universities, regularly send students or professors, and they publish. They know very well their rocks, so you should kind of contact them, cooperate with them, in order to gain better understanding of that area. Then perhaps in connection with these universities, you will like a place. You will then sample your rock. You will make a few field trips, sample the rock, take samples of the rock, and then take them for analysis to a laboratory. Analyze those samples, see how good they are, whether you like them or not. And once you have these samples, you kind of can construct a story. Now, how you decide where to go, that's maybe the art of the whole thing. The source rocks oftentimes, as I said, they were deposited in certain moments in time. Around 100 million years ago, around 200 million years ago. They are global, oftentimes. And so, with these notions, you can assess whether a certain part of the Earth will have good conditions, good rocks with those good conditions or not, by knowing the geology of that area.
Well, thank you, Fernando, for this practical talk and chat that you had with us in being so down to earth to explain difficult concepts or maybe sometimes unusual to some of us. We still have a couple of minutes, so I will leave the mic open for you so that you can do your shout-outs, you can express some concepts you didn't, you can talk. The microphone is open if you want to add anything about this or other things. This is a community radio, so the mic is yours.
No, thank you, Daniel, for bringing me. It's been great to be able to talk about all this. We know each other. We have been in places together exploring. All I would say is that geology is a very nice science. That there is really nothing like going to the field, like seeing those rocks, like seeing a sunset or a sunrise when you're there, being with colleagues, and kind of the voyages of discovery. The understanding of the past. In a congenial sort of environment with other people that kind of share the same passions, etc. So I don't know. I encourage people to look into geology, and especially if they can, not to forget about field geology, which is certainly the king of our specialties, our science, in my opinion.
Thank you very much. Thank you so much, Fernando. Fernando Sanchez, a very pragmatical explorer, great explorer here with us.
Yeah.
All right. This was a mini geology.